In this video, we're going to look at some linear transformations in R2 and R3 that have geometric interpretations. So included here are some of the linear transformations we're going to look at. So when we reflect about the y-axis, what happens is the y-coordinate stays fixed, and then we take the opposite of the x-coordinate. Right? So if x is positive, it becomes negative, and if it's negative, it becomes positive. And then similarly, when we reflect about the x-axis, the x-coordinate stays fixed, and we take the opposite of the y-coordinate. When we reflect about the line y equals x, the x and y coordinates switch places. So when we expand horizontally or vertically, so for horizontal expansion, the y coordinate stays the same, and then the x coordinate scales by a factor of k. And then similarly, vertical expansion, the x coordinate stays fixed, and then the y coordinate scales by a factor of k. And then what happens during horizontal and vertical shearing is that the farther away something is from the x or y axis, the more slanted it becomes. Okay, so let's take a look at some examples of these kinds of transformations. So basically what happens is for a set of points in the plane, to apply one of these geometric transformations, we just do the appropriate matrix multiplication, right? So we apply the matrix, one of these matrices A, to each of the points in the set. So for example, if I want to apply a horizontal expansion by a factor of 2 to the triangle with these vertices. So first let's look at what this triangle looks like, right? So negative 2, 1 is this point, 4, 1 is this point, and 1, 5 is this point. So we have this isosceles triangle. And okay, so now I want to transform this by doing a horizontal expansion by a factor of 2. Right, so horizontal expansion is this kind of matrix. So K is going to be 2. So my matrix A is going to be 2, 0, 0, 1. And so now to see what this triangle looks like after the transformation, I just apply the matrix A to each of these 3 points. Right, so 2, 0, 0, 1, apply to the first point, negative 2, 1. So the result is negative 4, 1. And then I apply it to the vector 4, 1. And then calculating it, it becomes 8, 1. And then finally, I transform the last point 1, 5, and it becomes 2, 5. Okay, so now I plot these for these 3 points, right? So negative 4, 1 is located here, 8, 1. So the coordinate axis here is not long enough, so let me just add a couple units. So 8, 1 is about here, and then 2, 5 is here. So what we see is this transformation by this matrix A transform this triangle into this triangle. So basically what the horizontal expansion by a factor of 2 is it keeps things the same height. As you can see, the height is the same, but everything is spread wider by a factor of 2. Okay, so this is the horizontal expansion. In this next example, we look at a horizontal shear by a factor of k equals 1. Okay, so just like before, let's draw the original picture to see what it looks like. Okay, so we have a square where the vertices are 0, 0, 3, 0, 3, 3, and 0, 3. So that's my original object. And now let's look at the transformation, right? So horizontal shear by a factor of 1. So the horizontal shear, the matrix has this form. So A is equal to 1, and then K goes here. K is 1. This is 0 and this is 1. Okay, so now, as before, I transform each of the vertices. So transforming the 0 vector with the linear transformation always goes to the 0 vector. So for the vector 3, 0, so this gives me 3, this gives me 0, so this vector stays the same. What about the vector 3, 3? So this is 3 plus 3, which is 6, and then this is 3. And then finally, I transform the last one, which is 0, 3. Calculating it, this is 0 plus 3, which is 3. 0 plus 3, which is 3. Okay, so now the 4 points are here, right? So these 2 points stay the same. And this one becomes 6, 3, which is here. And 3, 3, which is here. So now if I connect the vertices, it looks like this. So basically what happens is, because we're doing horizontal shearing, things that are on the x-axis stay exactly the same, but things that are farther from the x-axis get shifted over more. Right, so you can see that here, when we're not so far from the x-axis, it's only slightly shifted to the right, but as we go higher, it gets shifted more to the right. So that's basically what happens during a horizontal shear, right? So things that are farther from the x-axis get shifted more. Now we look at some geometric transformations in 3 dimensions. These 3 transformations are rotations about a fixed axis. So the first one here is a rotation around the x-axis by an angle of theta. This is a rotation about the y-axis around by an angle of theta. And this is a rotation around the z-axis by an angle of theta. So in each of these 3 matrices, you can see that the underlying 2 by 2 matrix here is the same as a rotation in the plane. Right, so again, this 2 by 2 matrices made by these 4 entries, and then this 2 by 2 matrix made by these 4 entries. And you can see that in this case, this applies to the second and third coordinates. This applies to the first and third coordinates, and this applies to the first and second coordinates. Okay, so what's occurring in these 3 transformations is that this one here fixes the first coordinate, which is the x coordinate, and then rotates the y and z coordinates. Similarly here, this fixes the y coordinate, and then the entries appearing in these positions rotate the x and z coordinates. And then similarly for this rotation. In each of these three types of rotations, what you can do is you can compose them together in various different combinations to get a more complicated rotation. Okay, so let's look at an example of a rotation of this type. Right, so we're going to rotate this tetrahedron specified by these four vertices by an angle of 30 degrees about the x-axis. So it's going to be this first type of rotation. So to first set up the matrix, I need to calculate the sine and cosine of the angle. So cosine 30 degrees is square root of 3 over 2, and sine of 30 degrees is 1/2. So what does that mean? So my matrix A, okay, so these entries should look like this, and then the rotation occurs in these four entries. Right, so it goes cosine minus sine, sine, cosine. So this is cosine, so square root of 3 over 2, minus sine, which is minus 1/2, sine, which is 1/2, and then cosine, which is square root of 3 over 2. Okay, so now that we've set up the rotation matrix, to calculate the rotation now, we just need to apply the matrix to each of these 4 points. Right, so for V1, we apply the matrix to the vector 0, 0, 0, but the transformation of the 0 vector is always the 0 vector. Now for V2, so 1 times 1 is 1, and then this 2 by 2 matrix only multiplies these two coordinates, but this is 0, 0, so this would be 0, 0. Now V3, 0, 1, 0. So what this does is, right, so this, when you do the matrix multiplication, this 0 applies to the first column, this 0 applies to the second column. And what this 1 does is it picks out the second column here. So the result is just square root of 0, square root of 3 over 2, 1/2. And then finally, V4, so basically what happens here is this 1 is for the first column, this 1 is for the second column, this 1 is for the third column, and when you do the matrix multiplication, basically this just means to add the 3 columns together, right? So 1, 0, 0 is 1, and this plus this is the second entry, so square root of 3 over 2 minus 1/2, and then last entry would be the sum of these two entries, so 1/2 plus square root of 3 over 2. Okay, so that's the transformation of the 4 vertices. So it's not so easy to draw in 3 dimensions, so I'm not going to try to visualize the transformation. However, if you've ever looked at 3D graphics on a computer or a cell phone or something like that, basically to set up the 3D graphics, a lot of these kinds of transformations are applied. So basically it just involves a lot of matrix calculations of this type.